Hello everyone, welcome to the third lecture of the fourth module, which is on CMOS inverters. So in the last lecture, we were discussing about the dynamic behavior of CMOS inverters. We were looking at, the different components that contribute to this load capacitance, and we were looking at how to calculate the delay and so on. In this lecture, we would be looking at different modes of power dissipation in the CMOS inverters. Disclaimers remain the same. So let us first discuss about the static power dissipation in a CMOS inverter. So what exactly is static power dissipation? So static power dissipation arises because of current between the supply rails, between VDD and the ground, those two supply rails, in the absence of switching, or when your output is at steady state. That is, your output is fixed at logic 0 or logic 1. Now, in CMOS inverters, the best part is that when your output is logic 1, your input is logic 0, that is, your N MOSFET is in cutoff mode there. So your Vin is logic 0, that is less than Vt of N. So NMOS is cut off when output is logic 1. Similarly, when your output is logic 0, then your input is logic high, that is your input is VDD, and that is greater than VDD minus mod of VTH of P. And therefore your PMOS is in cutoff mode. Since either your NMOS or your PMOS is in the cutoff mode, there is nothing connecting VDD and VDD and the ground. So ideally, if these are in cutoff mode, we assume that no current flows through them. And as such, there's no standby current between the VDD and the ground rail. And therefore, we say that there's no static power dissipation. Or we say that there's no electrical path connecting your supply and the ground because one of them is always cut off. Whenever your output is fixed at logic 1 or output is fixed at logic 0. Since that standby current is 0, that is, there's no current between supply and the ground, ideally we should have static power equals to 0. Because static power is what? Static power dissipation is simply VDD multiplied by I standby, which is being taken by the supply when output is at a fixed state. Right? It is at steady state, it's at logic 1 or logic 0. So, as I told, ideally, no static power should be dissipated in CMOS inverters. And this is a pretty good situation as compared to, using resistors as a load or using even biased MOSFETs as a load. We saw in those cases that there was a static power dissipation and that was huge. But compared to that, ideally, your CMOS inverter shows no static power dissipation. But even below cutoff, we know that, it's not the situation that, no current flows. So there are few components of static power dissipation, and that is because the real world is harsh. I mean, this is something which we consider ideally that below cutoff or in the cutoff regime, no current actually flows through the MOSFET. Reality is something different. Reality is harsh. And there are several sources of standby current or the static power dissipation, even in the CMOS inverters. So we'll be looking at 3 of those leakage mechanisms. One of them is pretty advanced. I mean, I don't know if it is a good idea to even discuss it with you, but I thought that I would include it so that some of you can at least understand it. I mean, I guess most of you will comprehend it. Most of you will comprehend it because it's not that difficult to understand. So let me just go ahead and discuss the first source of static power dissipation. So here it shows you the CMOS inverter. What I have drawn is, I have just drawn these body terminals. So what exactly are the body terminals? So body terminal of the N MOSFET here is connected to the lowest potential available, that is ground. And the body terminal of this P MOSFET is connected to the highest potential, that is your VDD. So as to, keep this VSB equals to 0 or not allow it to get forward bias. Because in that, if it gets forward bias, then what happens? Your essence of MOSFET gets lost, right? So we don't want these, junctions to be forward biased. The body source junctions to be forward biased. So body is connected to the minimum potential, which is ground here for NMOS, and body is connected to the maximum potential, which is VDD here for the P MOSFET. However, so this is something that we discussed earlier. However, if you look at the drain body junction, the drain is connected to Vout and your body is connected to VDD in one case and your body is connected to ground in the other case. So what we have, this body is P type and this drain is N type. So we have a parasitic PN junction diode over here, and the direction is because this is P and this is N, right? And reverse happens in the P MOSFETs. So we have drain as P plus, source as P plus. So this is P plus, right? And this is your body, which is nothing but your N-well. So this is N-type, right? So you see that here, this is basically the parasitic PN junctions formed because of the body and this source and drain regions of P MOSFET and the N MOSFET. And what can you say about their bias? So this PN junction here, the direction is for P here, P is here, N is here. Similarly, P is here, N is here. And this is connected to the most positive voltage VDD, and this is connected to the most negative voltage, which is ground here. So P connected to most negative voltage, you can say that this diode is either reverse biased or unbiased. When V out equals to 0, this is also 0, so this is unbiased. When V out is equals to 1, this is highly reverse biased, right? Similarly, if you look at this parasitic diode, what we have is when this is VDD, so when V out is equals to 0, this is highly reverse biased. And when this V out is equals to ground, then this is, when this V out is equals to VDD, then this is unbiased. So if V out is equals to logic 0, that is if V out is grounded, then what happens? This is unbiased, but this is highly reverse biased. So reverse saturation current will flow from VDD to the ground when V out is grounded, or it is at logic 0. Similarly, when V out is at VDD or logic level 1, then what happens? This is unbiased, but this is highly reverse biased. So reverse saturation current will flow from this VDD to this ground when V out is VDD to this ground. So in either case, these body and drain junctions are either reverse biased or they are unbiased, and reverse saturation current flows. Flows between what? Flows between either VD to this ground when V out is ground, or this V out when it is VDD to this ground, right? And what is that magnitude of current that flows? It's the reverse saturation current, which is pretty small. I mean, you can neglect it always. It's pretty small. And what is that leakage power? So it's simply VDD multiplied by IS, where IS is the reverse saturation current. Typically, the value of IS is in some picoamps. Therefore, this power is pretty small. It's less than nanojoules. It's somewhat in picojoules. So if this is in picojoules, then it's pretty small and you can neglect it as well. And why is this happening? Because you have these two reverse biased parasitic diodes. I mean, one of them is reverse biased at one time, but you have these reverse biased diodes. This is not dangerous at room temperature, but since this is because of thermal generation, I mean, since this reverse saturation current is because of thermal generation, so what happens? As the temperature increases, this IS increases exponentially. And as a matter of fact, at 85 degrees Celsius, IS increases by almost 60 times. And the typical operating typical operating temperatures of these ICs is close to 55 degrees Celsius. I mean, it's more than room temperature always. And it may get heated even to the extent of 85 degrees Celsius during runtime. So in that case, IS increases significantly, and it may contribute towards some leakage, but still it's pretty small. Even when it increases by 60 times, it would be some nanojoules itself. So that is something that you can still neglect, or that is something which you need not care about. But one more thing, there are several of these MOSFETs, right? There are some 1 million or 1 billion of these MOSFETs. So in that case, you have to care about it, right? Let's look at the second mode of static power dissipation in the CMOS inverters. And that is because of the subthreshold leakage, which I have been continuously talking about in the lectures, as well as in the discussion sessions and the tutorial sessions. So here this curve kind of shows you the transfer characteristics, that is ID versus VGS characteristics of two different MOSFETs. So this is one MOSFET, this is another MOSFET. So you see threshold voltage of this MOSFET is smaller, threshold voltage of this MOSFET is larger. And even below the threshold voltage, some current is flowing, right? Here some current is flowing, here also some current is flowing. And at 0 volts, at VGS equals to 0 volts, this current is larger. I mean, the leakage current of this transistor is larger, leakage current of this transistor is smaller. As a rule of thumb, larger the threshold voltage, lower the leakage current, smaller the threshold voltage, higher the leakage current. That is something that you should understand. And you see that appreciable amount of current flows even when VGS is less than VT. You see 10 to minus 7 amps flows at 0 volts, even when VGS is less than VT. And this is huge. I mean, this is not something which is, negligible. Here it's negligible. It's close to some picoamps when your VT is large, but when your VT is small, then it's not negligible, right? Now here, one more thing I would like to discuss. How are we actually calculating the threshold voltages here? So in the industry, though, they don't look at, they don't just plot it in the linear scale like this, and then they say that, okay, you find out the extrapolation to the x-axis. No, that is not how people do it. Because in that case, if you change the magnitude of this on a linear scale, then this threshold voltage definition changes. This threshold voltage changes. Similar to, the cut-in voltage of a diode. You just change the axis. I mean, you just change the magnitude of this axis in a linear scale, your extrapolated value will change. So that is not something which industries use for finding the threshold voltage. What they do is, or ideally, how we define the threshold voltage, we define it like the gate voltage at which the concentration of the inversion layer is equal to the bulk concentration. But concentration of inversion layer is something that is not measurable. You cannot measure it, by any technique in situ. I would say, if you have a MOSFET in your hand, you cannot measure the bulk concentration. You cannot measure not the bulk concentration, but the inversion layer concentration. So that is not something which is measurable, and that is just an academic definition. How industries measure the threshold voltage? The most common way of doing it in the industry is a constant current method. So what they do is, they just write that, okay, 10 to the power minus 7 amps into W by L, the gate voltage at which this current is reached, that is your threshold voltage. So for this W by L ratio, so here W by L is 10. So 10 to the power minus 7 into W by L is 10 to the power minus 6. So the moment current reaches 10 to the power minus 6, you get the threshold voltage. So this is how industries measure, or people in industry measure, the threshold voltage. They don't use extrapolation. They don't use, the definition that at VGS equals to VT, you have inversion layer concentration equal to the bulk concentration. They use the constant current method, 10 to the power minus 7 into W by L. There are other methods as well, which depend upon the transconductance. So if you look at the transconductance as a function of VGS, so your GM first increases and then it decreases. So the point where it starts to decrease, or the point where it reaches its peak, that is your threshold voltage. And that is called transconductance method of measuring VTH. There are like 8 or 9 ways of measuring this threshold voltage. However, the most easy way, or the industry, what industry preaches or what industry follows, is this constant current method, 10 to the power minus 7 W by L, and the gate voltage at which that current is achieved, that is your threshold voltage. Okay. And as I told you, large VT, you have small leakage, right? At 0 volts, you have small leakage. You have picoamps, currents in picoamps. But that also means small on-state current. Why? Because in on-state, the current depends upon VGS minus VT. So VGS remains same 1, but VT is large. So your on current is smaller. Similarly, small VT or low VT, what happens? Leakage current is large. However, what about the on-state current? Since that is dependent upon VGS minus VT, so that is also large. So rule of thumb, large VT or high VT, smaller leakage, but smaller on current as well. Small VT or low VT, larger leakage current, but higher on-state current as well. So industries, they always give you 2 variants of transistors. Whenever you talk about any technology node, they'll always prepare these 2 types of transistors. One would be high performance, which would be a low VT transistor. Why high performance? Because its on current is high. So the delay would be smaller. And low power transistor, why low power? Because its subthreshold leakage is pretty small. So the static leakage with this transistor, if you design circuits with this transistor, then the static leakage would be smaller. So depending upon the consumer requirement, whether they want a high speed or a low leakage, you have these 2 variants of transistor that every foundry provides for each technology node. Now, what exactly is subthreshold leakage? So even when your gate voltage is not equals to the voltage where your inversion layer concentration is equal to the bulk concentration, you have some, even below that voltage, even below that gate voltage, you have some amount of carriers, some amount of electrons in the inversion layer. That is called weak inversion layer. And even in that weak inversion mode, you have some carriers which can flow easily from source to the drain region, right? And therefore you have this kind of subthreshold leakage current. So industries, they always provide you 2 variants of these transistors. Depending upon what is the main focus of your product, you can use either a high performance device, which is nothing but a small VT or low VT transistor, or you can go for a low power device, which is nothing but a high VT transistor. Also, during runtime also, there are several tricks that these industries use in microprocessors. One of them is known as power gating. So what exactly is power gating? So at any point of time on a chip, all the gates are not being, switched on or switched off. Some of them are in the static mode, right? Even if you're making your gates with the help of high performance transistors, some of them would be in static mode. Only some of them would be switching, right? Not all would be switching at every time. So those which are not switching, what people do is during runtime, they power them down. How they power them down? They use these two sleep transistors, which are nothing but low power transistors, which are showing extremely poor leakage. They connect these logic circuits or logic gates not directly to VDD or ground. What they do is they insert these sleep transistors in between, which are nothing but low power transistors, which have extremely small leakage. So what happens during runtime? I mean, when they are switching, then the sleep is zero. So when the sleep is zero, this is turned on. This is also turned on because it's sleep dash. So sleep dash is like sleep is zero, sleep dash is one. So these are turned on. And this logic circuit having a pull-up network and a pull-down network is connected to VDD and ground when it is switching. But when it is not switching, when the other logic gates are switching, then what people do is, or what happens in the architectural level, this sleep dash is turned to zero. So when sleep dash is gone, like when sleep dash is zero, sleep is equals to one. So these two transistors, they go into the cutoff mode. And since they are using low power transistors, the leakage current is pretty small and a minimal amount of leakage current flows through this network. Even if this pull-up network and pull-down networks are made up of high performance transistors where the leakage current is high, since they are in series with these low power transistors, so effectively you can kind of control the leakage current through this, and the leakage current is pretty small. And this kind of system is called power gating. It is used in almost all the processors nowadays, and this power gating is something that is used to minimize the leakage power dissipation, because the levels of leakage that we are getting in modern transistors, that is pretty huge. So unless we do innovations in transistor as well as architecture level as well as circuit level, it's not possible to mitigate. So this is a kind of innovation at architecture as well as circuit level, because we are introducing these two extra transistors which kind of minimize the leakage current through this logic gates. Okay, so now that we know power gating, let us look at another leakage component, which is something which is very recent and which most people don't talk about when they are talking about this course, but I'll be including this in the course as well. That is known as gate leakage. So why gate leakage comes into picture? So ideally what we have is in any MOSFET, we have this metal, this oxide insulator, and then this semiconductor, right? It's a MOS. So we have metal oxide semiconductor. So we assume so far that the gate oxide is a perfect insulator and we have a COX there, right? We have an oxide capacitance there. But along with scaling down the channel length, we have to scale down even this gate oxide thickness so as to increase the field effect, right? So what is field effect? Field effect, whatever voltage you are applying here, how much of that is being coupled to the channel? Because that is something which is deciding how efficiently you are controlling the channel electrostatics, right? How efficiently you are able to invert the channel, how efficiently you are able to, put the channel in depletion and so on. So that depends upon the electric field between the metal to the semiconductor. And your insulator is something which is coupling that electric field, right? So a thinner insulator will give you a higher capacitance and it will couple electric fields in an efficient way. So that is the reason going for ultra thin gate oxides or ultra thin insulators in the gate oxide. However, the moment you reduce these thicknesses, the gate insulator doesn't remain, an insulator. So ideally, since it's an insulator, it should, no current should flow through it and it should show you infinite impedance, right? But what happens in ideal situation, as your thickness reduces below 5 nanometers, so why exactly input current is zero? Because if you draw its energy band profile of electrons, let me just draw it once. So if we draw energy band profiles going from the metal, to the oxide and then to the semiconductor, it looks something like this. So this is the metal, this is the oxide, and this is the semiconductor. Why is there a peak? Because oxides have a pretty high band gap, right? So the electrons here, they see a pretty high barrier in order to flow from here to here. Similarly, the electrons in semiconductor, they see a pretty high barrier when they want to flow from semiconductor to the metal. And as such, we say that current or electrons cannot flow between metals and semiconductors, right? Since there is an oxide in between. However, when the oxide thickness reduces below 5 nanometers, what happens? Instead of flowing over this barrier, they can also tunnel through the barrier. They can tunnel like this throughout the barrier, or in some situations, they tunnel only at this peak, only at this point, right? So now let me discuss about these two different tunneling mechanisms which we encounter when we are talking about, the gate leakage. So as I told, as the oxide thickness reduces, instead of going beyond the barrier like this, jumping over this barrier, the electrons can even tunnel through the barrier. So there are two different mechanisms of tunneling, and that depends upon the oxide thickness. So if the oxide thickness is larger than 3 nanometer, there is something which is called Fowler-Northam tunneling. So what happens? If the oxide is more than 3 nanometers, all these electrons cannot tunnel through this barrier. I mean, this barrier is thick enough for these electrons to tunnel directly. So what happens here is only the highly energetic electrons which are here, they can tunnel through this small barrier here, right? So the barrier thickness here is pretty small, right? Since the electric field is applied, so the energy bands are kind of bent like this. And the barrier effectively is thin here at the top. And it increases and then it remains constant throughout, right? So since the barrier thickness is kind of small here at the top, energetic electrons which are present here, they can tunnel here. And this is what happens in Fowler-Northam tunneling. It's tunneling through a triangular potential barrier. However, if the thickness is less than 3 nanometers, I mean, if this thickness is pretty thin, I mean, if it's pretty small, then all the electrons throughout this barrier can tunnel. And that is called direct tunneling. So in direct tunneling, all the electrons can tunnel from here to here. Whereas in Fowler-Northam tunneling, only the electrons which are highly energetic on top here, they see a lower, tunneling thickness or potential barrier or barrier width, and they kind of tunnel from this point to this point. And that is known as Fowler-Northam tunneling. It's not that necessary for this course, but I just wanted to, give a brief overview that if the oxide thickness is small, you cannot assume that its input impedance is infinite. It also consumes some current, and this current actually flows from the body to the input when mean equals to 0. Why? Because the body is connected to the highest potential. So body to input is like this is at a higher potential from this, and as such tunneling can take place from the body towards this metal gate. For the NMOS, since this body is connected to the ground, therefore when mean equals to VDD, then this electric field can lead to tunneling of electrons from the gate terminal from metal to this body, to the ground. So this is another kind of leakage mechanism which is prevalent in your MOSFETs. And as I also discussed in the tutorial section, nowadays what people are doing is, instead of reducing SiO2 thickness, they're kind of replacing it with two oxides. One, SiO2 0.5 nanometers, and on top they're adding a high K dielectric. Why high K? Because high K dielectrics, even with a higher physical thickness, they provide same effective oxide thickness or same electrical thickness. I mean, if your oxide thickness is large and your dielectric constant is also large, effective field remains same as that of SiO2. So physically, the barrier thickness is large. However, electrically, the amount of field that it couples remains same as that thin SiO2. This is something which is hard to digest, but at this time, I would just, request you to kind of take my words as it is and, try to learn about this high K dielectrics and how they work. In like, if you're interested, you can go through it, but take my words that, if you have a capacitor and its dielectric constant is larger than 1, then it couples electric fields better as compared to air. So if you have similarly, if you have a capacitor in which the dielectric constant is 3.9, which is SiO2, and if you have a capacitor in which the dielectric constant is 25, which is HFO2, hafnium oxide, then definitely for same thickness of those two dielectrics, the amount of electric field which will be coupled in this HFO2 based capacitor will be 6 times. So it goes as ratio of your dielectric constants. So if you have same thickness, same physical thickness, the electric field is 6 times high in HFO2 as compared to SiO2 capacitor. If you want same electric fields, then you can scale the physical thickness of this HFO2 capacitor by 6 times. So that is how you can work with this with a small physical thickness as well. And I told you even in the last discussion session or even in the tutorials that industry has now moved to this HKMG technology, high K dielectric metal gate technology. And the reason being that, as the these silicon oxide thicknesses have reduced, this gate leakage has become a really big problem, and that is why they want to replace this gate oxide with high K dielectrics. However, the individual leakage current is pretty small. I mean, it's in some picoamps, and therefore the overall leakage power is in some picojoules. Since there are a large number of these transistors, then we have to worry somewhat about this, because we have to the consumers give us some power budget, and then that power budget should contain even this gate leakage or even that diode leakage or the subthreshold leakage. So we have to kind of distribute these components and take into account these components as well. So in modern MOSFETs, gate leakage is kind of mitigated by the use of high K dielectrics. Now let us talk about the dynamic power dissipation. So dynamic power dissipation, when does the dynamic power dissipation happen? Whenever the output is switching. And we saw in our preliminary discussions that this power is taken or energy is taken from the supply only when the output goes from 0 to 1. So whenever the output goes from 0 to 1, it takes in some amount of power from the supply or some amount of energy from the supply. Let us say that F0 to 1 is the frequency of changing the output from 0 to 1. Then if F is kind of the maximum frequency of changing inputs, which is ideally synchronized with clock or the clock frequency, then F0 to 1 can be simply given by alpha 0 to 1 into F, where alpha 0 to 1 is the switching activity of the output. And that is the probability of the output going from 0 to 1. And that depends upon inputs which are being applied here, how statistically independent they are, and also on the type of logic gate, whether it is a NAND or NOR or an inverter. So typically alpha 0 to 1, if the inputs are biased equally, like probability of 1 at the input or 0 at the input is 0.5, then alpha 0 to 1 is P that the output is 0, that is 0.5, into probability that the output is 1, that is 0.5. So it's 0.25 for an inverter when its inputs are unbiased. That is probability of input being 1 or 0 is 0.5. And then the frequency of changing the output from 0 to 1 for that inverter will be 0.25 times the maximum frequency or the clock frequency. And the dynamic power dissipation, we have seen this expression multiple times, is simply given by F0 to 1, the number of the frequency of changing the output from 0 to 1 multiplied by CL into VDD into V swing. Why VDD into V swing? Because the charge equal to CL times V swing, charge equals to CL times V swing is deposited onto this load capacitor from this VDD. And what is your energy? Energy is simply Q times V. So what is Q? Q is CL times V swing. What is your V? V is basically VDD. So the dynamic power is simply given by F0 to 1 CL VDD V swing. This is your dynamic energy, and this is your frequency, and that is why you get a power here, right? And if you expand it further, it's simply alpha 0 to 1 F, which represents your F0 to 1 CL VDD, VDD minus VOL times F. And what is VOL here? VOL is simply 0. Sorry, this F is not there. I mean, this expression is wrong. So here it should be simply alpha 0 to 1 F CL VDD into VDD minus VOL. And what is VOL? VOL is 0. So it is alpha 0 to 1 F CL VDD square. So for CMOS inverter, since V swing is VDD, you have this P dynamic as alpha 0 to 1 F CL VDD square. That's it. This F is not there. I mean, this is incorrect here. And the dynamic power dissipation used to dominate the power dissipation in the CMOS inverters till 2000s or 2005. But then as you scale down these MOSFETs, the other static leakage components, they became significantly dominant. And nowadays it's the static power which dominates. And people have to go with tricks like this high K dielectric or using power gating and so on to reduce the static power dissipation. Is this load capacitance? We should use minimum sized N MOSFET and P MOSFET because their intrinsic capacitance also kind of are the components of this overall load capacitor, apart from the wiring capacitances and the fan out capacitances. However, we saw that to achieve symmetry, we have to make this P MOSFET width beta times as compared to this N MOSFET, and beta is typically 2. However, it was also noted in the last lecture that we can kind of reduce the delay by doing what? By increasing the width of this P MOSFET. But that came with a caution, right? That came with a caution that that helps us in reducing the delay only when what? When the CL is kind of dominated by extrinsic components. When the CL is dominated by the intrinsic components, then increasing this beta only increases CL. It doesn't help you much with reduction in the delay. In fact, it worsens the delay. So in order to minimize this CL, use minimum size MOSFETs and go for scaling only if the CL is not dominated by extrinsic, it's not dominated by intrinsic components, it's dominated by wiring and the fan-out capacitances. So the designers also, use some tricks during runtime, like this dynamic VDD scaling. So what they do is, whenever you see that the battery is running low, your operation of laptops or mobiles, they get somewhat slower. So what happens is, they do this dynamic VDD scaling, that is, they reduce the VDD at that time. When the battery is draining large, I mean the battery power levels are low, then they use a reduced VDD. If you reduce VDD, you are quadratically going to reduce this dynamic power dissipation. But if you reduce your VDD, the currents that are flowing into these load capacitors, they become small, and as such the speed somewhat degrades. So at lower battery levels, you may have seen somewhat delay in your processor performance. So that is because they have dynamically reduced the VDD just to reduce the dynamic power dissipation. Also, by employing tricks like parallelism or like instruction level parallelism, what they can, or pipelining, what they can do is they can change alpha 0 to 1 and this F, I mean effective F, not exactly the maximum clock frequency, but effective F that the gates see, that can be changed by using tricks at architecture level. And also alpha 0 to 1 is something that you can change by changing the different dependencies of these inputs, whether they are statistically independent or not. You can make their probabilities different in order to use or in order to reduce alpha 0 to 1. So there are a lot of things that these designers can do. And despite these processes being so semi-automated, you need so many design engineers. The need for design engineers is just because these tricks cannot be implemented on all the chips by AI or whatever, automated systems. You need people to kind of think about individual circuits, individual requirements, and then play with these tricks and find out a way forward. So that is why design engineers are required in huge amount, and they will continue to be in demand, because these tricks can be applied only by humans. I mean, you can train your AI model, and now precisely that is something which people have started doing. I don't know if you read, like if you have seen that in the news or not, but around a week ago, these companies, NVIDIA, Intel, IBM, they came up with a conclusion or consensus that now they'll be designing chips with the help of AI. So they're trying to make this process fully automated. Now we'll require more of ML engineers than the design engineers if what they're going to do is successful. So it came in the Forbes magazine that now the chips will be designed by AI and not by human beings. You can go through it if you are interested. Okay, so after discussing this dynamic power dissipation, let us discuss another important aspect which we have neglected till now, which is and just wait a second. Before going to that, let us first discuss about this alpha 0 to 1, how we calculate it. So let's say this is our clock. So our clock is going from 0 to 1, 1, 2, 3, 4, 5, 6, 7, 8 times. And how many times is the output signal going from 0 to 1? 1 and 2. Since the output signal goes only 2 times from 0 to 1 and clock goes 8 times between 0 to 1. So the probability, or this alpha 0 to 1, that is switching activity, is simply 2 divided by 8, that is 1 by 4, which is 0.25, which is the typical value for inverters when its inputs are statistically independent. So that is how we typically calculate alpha 0 to 1. And this is something which you guys should know. And now let us look at something which we have been ignoring till now. Even while discussing the delays and all, we have been neglecting this. And that is, in our circuits, we have finite rise and fall times. It's not a step input. We have been discussing the cases for step input, right? While calculating TPHL or while calculating TPLH, we have been discussing about step inputs, but in real world, these transitions are taking finite time. Let's say that transition from T1 to T2, input signal going from 0 to 100 takes TS, which is a finite time. And for simplicity of analysis, we are assuming that there's a linear relationship between time and applied voltage. That is, At t equals to T1, voltage applied is 0. And at t equals to T2, when Vin becomes VDD, the applied voltage linearly increases from 0 to VDD. And in between, it goes through VTN, VM, VDD minus mod of VTHP, and VDD. So the relation that we are assuming between the voltage and the time, it's linear. Now, as this input voltage goes from 0 to VTN, and MOSFET is on, and MOSFET is in the cutoff mode. So no current flows between your VDD and the ground. So till that point, no current is flowing between VDD and ground. But the moment this input voltage reaches VTN, this MOSFET is out of cutoff, and this P MOSFET is already out of cutoff. It is in the linear mode, right? This P MOSFET is in the linear mode here. When Vin is equals to VTN, then this P MOSFET is in the linear mode, and this N MOSFET is just out of cutoff, and it is in saturation. So the moment Vin increases beyond this VTN, both of these transistors are out of cutoff. This is in saturation, this is in linear. Then at Vin equals to VM, both of them go into the saturation regime, right? And maximum current flows between the VDD and the ground, because both of them are contributing current. Both are in saturation regime where the current is maximum, and then maximum amount of current flows between VDD and ground, because VDD and ground, they are now connected with two, closed switches, I would say, because both of them are kind of on. They are out of cutoff. They can conduct some current, huge current actually. Then when the Vin increases to VDD minus mod VTHP, what happens? This is still on. This is in linear mode now, and this goes close to saturation mode. So even below Vin equals to VDD minus mod of VTP, this is in out of cutoff. This is in the saturation mode, and this is in the linear mode, and some amount of current flows between VDD and ground, and that is called short circuit current. This short circuit current is maximum when Vin is equals to VDD, like when Vin equals to VM. Then both of them are in saturation, and they drain maximum amount of current from the VDD to the ground. However, just above VTN and just below this VDD minus mod of VTHP, these currents are pretty small, because now these transistors, like for here, NMOS is going into cutoff, here PMOS is going into cutoff. So if you look at the current profile, the current is maximum close to VM, and it goes 0 towards VTN or VTP, VDD minus mod of VTHP. And that I'm talking about the current between VDD and the ground, when both of them are out of cutoff. So because of this finite rise time as well as finite fall time, what happens in between the voltage, input voltage between VTN to VDD minus mod of VTP, both of these transistors are out of cutoff, and they can supply current between VDD and the ground through these two MOSFETs. So this current is called short circuit current, and this short circuit power dissipation is also significant contribution to this energy dissipation. And we'll calculate the exact values later. But first, let us see this diagram in detail. Let us say that the signal transitioning time, that is the time which it takes to go from zero, input takes to go from 0 to VDD, that is T2 minus T1, is TS, that is signal transition time. Now, as we defined our rise and fall times as value going from 0.1 to 0.9 times VDD, so this TR is equals to TF, and it is nothing but 0.9 minus 0.1, that is 0.8 times TS, assuming a linear relationship. So this rise time and fall time are 0.8 times the signal transition time between 0 to VDD, assuming a linear relationship. Now, fraction of voltage for which this short circuit current is flowing, or fraction of voltage for which these two MOSFETs are out of cutoff, what is that? It is VDD minus mod of VTHP minus VTN divided by overall voltage, that is VDD, right? So these two MOSFETs are out of cutoff in a voltage range which is given by VDD minus mod of VTP minus this VTN. And what is the fraction of the overall voltage? Overall voltage is VDD, so it's VDD minus mod of VTP minus VTN divided by VDD. So for this fraction of VDD, these two MOSFETs are out of cutoff, and they are contributing to the short circuit leakage. So the amount of time, assuming a linear relationship between voltage, applied voltage, and the time, the amount of time for which the short circuit leakage current flows, what is that? That is simply TS multiplied by the fraction of voltage for which these two MOSFETs are out of cutoff, right? That is simply TS divided by VDD into VDD minus mod of VTP minus VTN. So assuming linear relationship between time and applied voltage gives us this very easy relationship, which is relating your time for which this short circuit current is flowing, and that is simply TS, which is the signal transition time, which can also be represented in terms of rise and fall times, multiplied by the fraction of voltage swing for which these two MOSFETs are out of cutoff. So this is an important concept, and this is a pretty easy thing just because we have assumed a linear relationship between time and applied voltage. Now let us look at the current profile. So current profile also we have assumed a linear profile because this makes our life much simpler. And this is actually in reality it's quadratic, right? What happens at VTN? No current flows, and at VDD minus mod of VTP, no current flows because here PMOS goes into cutoff, here NMOS is in cutoff. Maximum current flows when mean equals to Vm, and both are in saturation. So this kind of profile is, for first-hand calculations, you can assume this kind of profile. Now, I see this is the short circuit current. So maximum short circuit current is present when mean equals to Vm and both transistors are in saturation. Now, the charge which is moved per cycle, I mean, this is one cycle where, first we go from 0 to 1 and then we go from 1 to 0. So in one cycle, the charge which has moved from VDD to ground is simply what? This area of these two triangles, right? And what is that area? That area is simply half into ISC, half into base into height, right? So height is ISC. So half into ISC into this time for which this short circuit current flows. So time for which this short circuit current flows is TS times VDD minus VTN minus mod VTHP divided by VD. This is what we discussed in the last slide, right? And 2 comes because we have 2 such triangles. Now this TS can be represented in the form of TR and TF as well, the rising time and falling time as well. So this is simply half ISC max rise time plus fall time divided by 0.8 VDD minus VTN minus mod VTP divided by VDD. This expression, since TR equals to TF is equals to 0.8 of TS, we can also replace this TS with this rise and fall times because that is something which is measurable. And then we can relate this charge, which is actually moved from VDD to ground, as half ISC max, TR plus TF by 0.8, and then the fraction of voltage for which this short circuit current, fraction of voltage swing for which the short circuit current is flowing. Now, what exactly is the energy? Energy is simply the charge multiplied by the potential difference across which it has been taken. And that is simply VDD times this Q VDD to ground, right? That is the energy dissipated basically. So energy dissipated is something which is energy dissipated in moving this charge from VDD to ground is simply ESC, E short circuit, which is VDD times this charge. That is simply half VDD ISC max TR plus TF by 0.8, and this fraction of voltage swing for which the short circuit current is flowing. Short circuit power dissipation can be represented in a similar way to that of the dynamic power dissipation by just multiplying this ESC by F into alpha 0 to 1, that is frequency output going from 0 to 1. This is similar to that of the dynamic power dissipation, and this is for one cycle, right? This is for one cycle. Now, this short circuit power actually used to dominate the dynamic power dissipation. In the beginning, this short circuit power is actually used to dominate the dynamic power dissipation. It was even larger than the dynamic power dissipation. And you can also club this with P dynamic by replacing this expression by an additional capacitance parallel to CL. And if that capacitance you represent it by CSC, that is short circuit capacitance, if its magnitude is TS ISC max by VDD, then your dissipation, like dynamic power dissipation component, I mean this formula for dynamic power dissipation, this thing, here, you just have to replace this by CL plus CSC, then VDD square. And that will give you what? That will give you power dynamic plus power short circuit. Now this short circuit leakage current also depends upon the value of CL, the magnitude of CL. That is a load capacitor. How? Let us see that. So let us take 2 cases. First, in which the load capacitor is quite high. That is, this circuit or this inverter poses a significant delay. And on the second right-hand side, we take the case when you have a very small capacitive load. So let us take the first case when you have a very large capacitive load. So as the input transitions from 0 to VDD within a time interval Ts, your input changes from 0 to VDD, right? And hence your VSG the moment it goes from 0 till VDD minus mod of VTHP, this PMOS is out of cutoff. But since this circuit is not reacting immediately, I mean, since the delay is pretty large, the output doesn't immediately go to, once the input goes from 0 to VDD, the output doesn't immediately grow from VDD to 0. What happens? The output remains at VDD for some time. And why it remains? Why it remains at VDD for some time? Because of the delay that this circuit is producing. And this delay is proportional to CL, which is pretty large. So even when the input is transitioning from 0 to Vin or 0 to VDD and taking time TS, if the output doesn't react within the time interval, that is, the output remains fixed, the effective VDS of this PMOSFET remains 0, right? Since this is VDD, this is also VDD, so effective VDS is 0. So if the output is pretty delayed in reacting to the input, or if the rise time of the input is quite small as compared to the fall time of the output, then what happens? Then effectively VDS equals to 0 during this transition and no short circuit leakage current flows through it. So if the output fall time is significantly larger than the input rise time, then short circuit leakage current is significantly minimized. Now let us take the case for small capacitive load. So for small capacitive load, this delay is pretty small, and the moment this input goes from 0 to VDD, the output reacts sharply, and the output voltage changes significantly. So even when this goes from 0 to some value, the output has started reacting, and as such, effective VDS is large, and during transition itself, effective VDS can be VDD, right? And in that case, short circuit leakage current will be pretty large. So in case you have a large capacitive load, your output fall time would be output fall time would be large, but your short circuit current would be minimum. Whereas when you have a small capacitive load, then your output fall time would be small, but your short circuit leakage current would be maximum. So we arrive at this relation or this conclusion that the short circuit energy dissipation can be minimized by making output fall and rise times larger than the input rise and fall times. Why? Because in that case, output doesn't react to this change in the input, and as such, like for some time, it doesn't react to this input change, and as such, its VDS remains equals to 0, and as such, one of the transistors remains at cutoff. So in that case, what happens? Short circuit current is minimal, and as such, or it's 0. So in that case, short circuit, this power dissipation can be minimized. However, if you are making large load capacitors, then what happens? In such cases, this load capacitor is kind of input to the other gate, right? In a chain of such gates. So in digital circuits, typically one gate drives the other. So the CL will be present as the input capacitance to some other gate, right? So that simply means that, you are slowing down the circuit operation, and you are kind of, increasing the transition time for the next stage of the logic. So if you're increasing the transition time, you're kind of increasing the short circuit leakage for the next stage of the logic, right? So the short circuit leakage flowing in the fan out circuit is increased, and also you're making the circuit pretty slow. So these are two, artifacts of using a large capacitive load. So typically how people deal with this is they tend to keep the rise and fall times of all nodes in the circuit close to same. I mean, the rise times and fall times of all circuits of all nodes in the circuit, they tend to match them. And they try to make these rise and fall times as small as possible, close to that steep slopes. How? By inserting signal regeneration circuits, which are also known as buffers. So buffers are nothing but two inverters placed in series. And because of their regenerative property, what they do, even if this is, changing in a quite, even if it is changing gradually, because of that regenerative property of these circuits, it helps in achieving a pretty, steep kind of output pulse, just because of this regeneration property.